another video. Hope you're ready to flex those brain muscles. Today, as you can see, I'm on campus. I'm in a different location. I figured I'd take advantage of this big whiteboard and we'll talk about transformations of quadratics. Just warning you, this is going to be a long video, right? This is a pretty, there's a lot to this topic. There's a lot to it. So I'm going to talk about it all, and I may split it up into two parts if it's super long. But let's go ahead and get right into it. Hopefully everybody knows what a quadratic is and you've seen standard form and vertex form. If not, I have some videos on that stuff. Hopefully you know what a parabola is, right? What a basic parabola looks like, what a vertex is, okay? These are the kind of the things we need to have going into this video. But basically what we're doing when we do transformations of quadratics is we're applying different transformations to our parent function f of x equals x squared. This is our parent function. So we can build off of this function, and as you can see, these are different things being done to the x squared, different changes being made, and we're going to relate all these things to come up with some general rules for how we can use these transformations to graph quadratics easier, right? And that's the idea of what transformations are useful for, is graphing these things. It becomes less tedious if we can identify some patterns and some general rules about what our a does, for example, what our h does, what our k does, right? And that's part of the reason why we, convert from standard form to vertex form, is to graph quadratics easier, okay? And sometimes we're even given quadratics in vertex form or in a form like this, and it's easier to apply these transformations than it is to like FOIL it out and try to graph it some other way, okay? So let's go ahead and get into it. We're gonna compare this parent function, f of x equals x squared, which I drew a rough sketch of here. And we're gonna compare this function to these other functions and see if we can notice some patterns and come up with some general rules. So let's look at example 1, f of x equals x squared plus 2. So what's happening is 2 is being added to f of x, right? I have f of x equals x squared here, and here I have f of x equals x squared plus 2. So f of x is what? My outputs. It's kind of like my y, right? So my outputs are getting 2 added to them, okay? So what do you think is going to happen? And this is the clearest, easiest transformation to see, in my opinion, is that this is going to shift vertically 2 units, right? Plug in 0 to x squared, and I get out 0. Plug in 0 to x squared plus 2, and I get out 2. Any number I plug in for x, this example 1 is going to be, the output's going to be 2 units higher, okay? And you can prove that to yourself. Try a bunch of examples if you want, but let's go ahead and graph this. We're just going to shift up 2 units, 1, 2, and we're drawing the exact same parabola, the exact same U shape. The only difference is we've shifted up 2 units. And again, these are sketches. I'm really bad at drawing accurate, nice looking, pretty graphs, but as you can see, I've shifted up 2 units, so let's go and write this. So vertical shift, that's what we call this, vertical shift by 2 units. Okay, vertical shift. So in general, what? K shifts vertically. This shifts our quadratic vertically. And depending on what the k is, determines how much it shifts vertically, right? So what do you think is going to happen if our k is negative? In other words, if I have like x squared minus 3, it's going to shift vertically but shift down, right? So if k is greater than 0, we shift up vertically. And if k is less than 0, we shift down vertically. Hopefully y'all can see that. So now we've come up with a general rule for k, for something being added to f of x, basically, right? But now we see something added to, instead of f of x, being added to x, right? This is x squared, this is x plus 3 squared. The 3 is being added directly to the x. So what do we think is going to happen here? And most people think that it's going to shift horizontally, and they're correct. But a lot of people think that it's going to shift horizontally to the right by 3 units, which would be incorrect. It actually shifts to the left. And the way to think of this, and the way I remembered it, early on learning this, is when the shift is being applied to the x, it does the opposite of what you'd think it'd do, right? But we can prove to ourselves why, and let's go ahead and graph it. So I have to erase first I'm going to erase my x squared plus 2. It wasn't very good to begin with. I apologize. I'll try to make this x plus 3 squared better. Redeem myself here, right? So, yeah, so like I said, it's going to shift to the left 3 units, but why? Well, look what happens when I plug in 0 to my x squared, I get 0. My vertex is at 0, 0, right? What do I have to plug into this to get out 0? I have to plug in -3, right? When I plug in -3 for my x, so I go down here to 1, 2, 3, -3, what happens? I get out 0 for my f of x, right? So my vertex is here at -3, 0. So the way I think of it, you know, if you want to think of it differently, then it's the opposite of what you think if you want a clearer idea. The way I think of it is that I have to plug in 3 less to x to get the same output for my parent function. So that's why I shift to the left 3 units, right? Because for x, I have to basically reduce my x by 3 units in order to get the same output that this parent function gets, okay? Maybe that makes sense, and if it doesn't, just remember it's the opposite of what you normally think, all right? So again, this is the same parabola, that same U shape, and the same really bad drawing here. I'm so sorry. Good Lord. Being a math major, you'd think I'd have this better. Okay, but yeah, we've shifted to the left 3 units, so we call this a horizontal shift. Horizontal shift. And this I should have put up, right? I should be specific. Horizontal shift, this is left. This is left 3 units. Okay, so in general, what do you think for our h? Can we write a general rule here? Well, let's see. In this case, our h is actually negative because this form is x minus h. We have x plus 3, so we have x minus -3. So this shifts horizontally. Let's see if I have room here. Shifts horizontally. And what do we think? When k, it's actually a similar idea as this. When our k is less than 0 in this case. When k is less than 0, we shift to the left. If k is greater than 0, we shift to the right. Hopefully y'all can see this. K is less than 0 in this case. Our k is -3, right? So we shift to the left. If k is greater than 0, we shift to the right. So, and this makes sense on why hk is our vertex, right? Because if we apply a shift, if our h is 2 and our k is 3, we have x minus 2 squared plus 3. So we're shifting vertically 3 units and we're shifting to the left 2 units. So our vertex moves to 2, 3. So now we're kind of making a connection between vertex form and finding the vertex, or making a connection with, you know, applying transformations to graph quadratics. So that's kind of cool to be able to connect those. So let's go ahead and move on here. Now we have 3x squared. So now what's happening? Well, we're taking we're plugging in for x, and whatever's being plugged in for x is being squared, but in this case it's being multiplied by 3, okay? So really what we have is all our outputs are 3 times what they normally are, right? This we have x squared, now we have 3x squared. So what do you think is gonna happen? Well, first I have to erase my last shift, and I'm gonna keep my x squared here. All right, so I'm gonna erase that last shift. My x squared stays here. Okay, so what do we think is gonna happen? Well, if I'm taking all my outputs and I'm multiplying them by 3, everything's being shifted kind of up, but the way this is described is as a vertical stretch. We're stretching vertically. So my vertex is still the same, right? There's no shifts to the left or right. There's no shifts up and down. My vertex is still the same. But look what happens. Let me plug in 1 for x here. I get 1 squared, that's 1. If I plug in 1 for x here, I get 1 squared, that's 1 times 3, that's 3. So all my values are being pulled up, basically. They're being stretched. That's the way I think of it, at least. So we have the same parabola. It's just skinnier. It's being stretched up, right? It's still a U shape, but it's being pulled up. It's being stretched up. So we have a vertical stretch, and we usually say by a factor of 3. By a factor of 3. By factor of 3. That's what we normally say. Let me fix that. By a factor of 3. So let's go ahead and write, let's see, our a. This is our a in this case. Our a is 3, right? But I want to wait till we do a couple more examples before we write the rules for that, okay? Let's actually go ahead and on the same graph, we can graph 1/3 x squared, okay? Because it's a similar idea. We still have an a. In this case, our a is 3. In this case, our a is 1/3. And maybe we'll even graph negative 2x squared, all in the same thing. So I can grab a different color here. So the green is my x squared, the red is my 3x squared, the blue will be my 1/3 x squared. So what do you think is gonna happen? Well, I'm plugging in for x is getting squared, and then it's being multiplied by 1/3. So instead of stretching vertically, what am I doing? Well, we call this compression. We're pressing everything down, right? Because think about when I plug in 1 for x. I square it and I get 1. That's for my parent function. But in this case, I square it, I get 1 times 1/3. So all my values are below the parent function, right? Think of compressing. Think of like flattening it out, squishing it. So that's what's happening to my parabola here, is it's coming out and it's being vertically compressed. That's the way we think of it. So we have a U shape that's being vertically compressed, and this way it's coming out this way. And we say vertically compressed by a factor of 1/3. So, I mean, I think you get the by a factor of 1/3 part. Vertical compression, I'll just write. Vertical compression. So let's look at example 3 and 5 and kind of see if we can come up with some general rules, okay? So we have what? A vertical stretch. Vertical stretch when what? Our A was greater than 1. But in this case, we're actually going to write absolute value, and we'll see why in a second. Okay? Because we're going to learn that when I have negative 2x squared, I still actually have a vertical stretch. There's also just one more component to it, and we're going to add more still. So what? Vertical compression. Vertical compression is when what? The absolute value of A is less than 1, right? And that basically means A is between negative 1 and 1. A can't be 0, obviously. So absolute value of A is less than 1. So I guess technically greater than 0, because my A can't be 0, or all this is gone, and it's not even a quadratic, okay? But you won't have to worry about that too much. You won't see cases where A equals 0. All right, so let's look at example 4, and let's see if we can come up with a rule for what happens when A is negative, right? Because now my parent function, I'm plugging in numbers. No matter what I plug in, negative numbers, positive numbers, all my f of x's are greater than or equal to 0, all my outputs, right? So in this case, what's going to happen? Well, everything for x squared, anything squared is always positive, but now we have something that's always positive being multiplied by something negative. So all my outputs are going to be negative now, okay? So what happens here actually is that if A is negative, let's write a rule for it. This actually still has a stretch by a factor of 2, right? So it still has a vertical stretch, but we're just going to say it opens downward, right? Opens down. And what I mean by open down is we have this parabola shape. In these case, all of these open up, right? They're all opening up. That's the way I think of it, open up, right? In this case, now we have something that opens down, and we also have a stretch. So we're going to apply both and draw something a little bit like this, okay? So if we want to finish off the rules for A, what can we write? Well, we can write if A is greater than 0, meaning positive, then the parabola opens up. And when I mean opens up, I'm talking about the parabola, right? The U shape. It either opens up or down. And if A is less than 0, the parabola opens down. So I understand this is kind of a lot of rules and maybe a little overwhelming. That's why I'm going to make sure we get plenty of content on this channel about this particular topic. So we're going to do a lot of examples. If I have to spread this out into a 5-part video series, I will, right? Because I want everybody to get the practice they need, get the understanding they need. Hopefully get a little bit comfortable with quadratics in standard form and vertex form, converting between the two, graphing them, kind of noticing what happens when you apply different transformations. So we're going to get into a bunch of examples. Hopefully this video has helped so far. This is kind of hard stuff to explain sometimes, so I'm doing the best I can, but hopefully this video is helping.